in this video, we are going to talk about the sign magnitude representation, okay, of decimal numbers by using binary numbers. Okay, so in sign magnitude number system, okay, sorry, it's not a number system, it's a representation method, the way you represent a decimal number by using the binary numbers, okay, which uses the binary numbers. Okay, so as the name suggests, okay, it has a bit for sign and other bits for magnitude. Okay, so that's what we call sign magnitude system. So sign magnitude system of representation. Well, what we do here is, well, normally what we do here is the first bit, okay, the first bit, or normally what we call is the most significant bit. Okay, I'll explain it in another video what is the most significant number or digit. Okay, for now, just keep in mind the first bit is allocated for sign. Instead of saying positive, we'll use the bit 0, and instead of saying negative, we'll use the digit 1 to represent that meaning. Okay, and sign magnitude representation has different methods. We have 4-bit sign magnitude representation, 8-bit sign magnitude representation, 16-bit sign magnitude representation, even 32-bit sign magnitude representation. There are many, but what we are going to focus here is 8 bits one. Okay, what we are going to focus here is 8 bits one. So the other 7 bits are allocated for to represent the magnitude of the given decimal number. Okay, so since we have 7 bits, which means we can represent 2 to the power 7 numbers. Okay, so the common misconception among students, okay, including myself, when I studied first time, is I thought, so since we have 2 to the power 7, this means I can represent 128 numbers, and we have positive and negative. So I can say we are going to represent from 128 to negative 128. That's what I thought. That's what I thought. But the thing is, okay, the thing is, we can't actually represent from 128 to negative 128. It's not possible. Okay, so what happens is, okay, you can represent from 0, 0, 0, 0, 0, 0, 0, 0 to, okay, 0, 1, 1, 1, 1, 1, 1, 1. Okay, so I'm just saying the positive regarding this is because the first bit is, we know it's for sign. Only the other 7 bits are used for the representation of the number. Okay, the magnitude of the number, not the sign. So here, what happens is you're starting from 0 and you're ending at 127. Okay, just quickly convert it and see. Okay, quickly convert it and see. So we are starting from 0 and ending at 127, which means we have started from positive 0 to positive 127. What happens in the negative part? Well, it's the same story. We have 1, 0, 0, 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1, 1, 1, 1. Okay, this is negative 0 to negative 127. So we are not representing 128 to negative 128. We are representing from positive 127 to negative 127. Okay, so here you can clearly see why this is not a proper method to represent numbers. Why? First of all, we have 2 zeros. Do we have 2 zeros in mathematics? No. We have only 1 0, and that 0 is 0. There are not positive 0 and negative 0. There is only 0, right? So that's the main disadvantage. And the system actually is inefficient in multiple ways because the addition and subtraction is choke when you use this method. Okay, it's a complete choke. So we don't use this for normal representation. Even in Python, they use 2's complement. I'll explain it in the future because that's what I'm going to explain tomorrow. So 1's complement and 2's complement. So sign magnitude is not actually a proper way to represent numbers. It's inefficient. The arithmetic circuits, the arithmetic functions that we use are not proper in the sign magnitude representation. And most importantly, if you consider this, we have better ones. So we don't normally use this. Okay, and it requires circuits, very arithmetic circuits. So this is normally used for digital and analog conversion. That's it. Okay, so this is the basic theory that you have to know. Now we will do some practice questions. Yeah, we'll do some practice questions. We will convert some decimal numbers to sign magnitude representation and sign magnitude represented numbers to decimal numbers as we normally do. Okay, So first of all, let's say we have to represent positive 35. We have to represent positive 35. Well, positive 35 can be represented in binary. Okay, the decimal number 10 to the base 10 can be represented as we have 32, not 16, not 8, not 4, yes 2, and yes 1. So this is the binary equivalent of 35 to the base 10. Okay, since this is positive, okay, now we are coming to the sign magnitude representation. Okay, now we are coming to sign magnitude representation. Since this is positive, we have to make sure we use 0 here. And here only we have 6 bits. Here we have only 6 bits. So keep this in mind. This is a very important thing that we do in representing numbers when representing numbers. Okay. This will be very useful in even networking. Okay. The thing I'm going to say, we need 7 bits. We have 7 bits. Okay. And we have only output for the 6 bits, the last 6 bits. So 1, 1, 0, 0, and 0, 1. What am I going to do with the excess bit that I have? What you have to do is you just have to put a 0 there. Okay. Not a 1, not a 1. You have to put a 0 here. That's all you have to do. This is how you're going to do the sign magnitude representation. I mean, this is easy, right? So we'll just go to other examples. So let's say we have 79. Well, that will be equals to 64. 32 is not, 16 is not. But since we need only 15 more, so 8, 4, 2, 1 to the base 2. So the sign magnitude representation will be, since this is a positive number, we need 0 first, and we will write down these 7 bits. Since we have 7 bits, you don't have to add another digit. Okay. Since we have 7 bits here itself, we don't have to add here. But here, since we have only 6 digits, we have to use one more binary digit or bit. Let's say we have plus 3. Well, that is equals to 1, 1 to the base 2. What we have to do is we have to add more zeros. Since we have 2 bits here, we have to add 5 zeros. That's all. Since this is positive 3, so here you have 0 and then 5 zeros, which will be followed by 1 and 1. That's it. Okay. So this is for sign. This is for magnitude. That's why that we call it as sign magnitude representation. Let's have plus 119 also. So that will be equals to 64, 96, 112, 120. So we don't have 8. So yeah, that's it. So the output will be, since this is positive 119, it will be 0, 0, 0, 1, 1, 1, 0, 1, 1, 1. Okay. Well, you can't put 2 here because this is not binary. Okay. This is not binary. This is sign magnitude representation, which uses binary. Okay. So you can't put 2 there. Okay. Cool. Now let's do for negative numbers. It's the same drill. Okay. It's the same drill. So negative 59. Well, we can say 59 can be represented as, when you have negative, don't get confused. Okay. Just convert the magnitude first. So magnitude can always be positive, right? So 59 is, 32, 48, 56, more 60. So 59 to the base 2. Okay. So this is 59. So we can't say negative 59. This is equals to 59, the magnitude. Since this is a negative number, you have to use a 1 here. Then we have 111, 011, which means 6 bits. Well, here also you have to fill it with a 0. Then you can use 111, 011, and that's the answer. If you have minus 79 or something, well, we can't use 79, we used it already. 99 to the base 10. Well, we know 99 to the base 10 is equals to 64, 96. We don't need 60, we don't need 4, 99 to the base 2. Okay, so 99 to the base 10 is this, and since this is a negative number, you use the 1 first, then we follow it with the other numbers. That's it. Okay, cool. So these examples are enough. Now we will convert from sign magnitude to decimal numbers. So let's say we have 0, 1, 1, 1, 1, 0, 0, 0. Well, we have 8 bits. So the number represented here is, since this is 0, first bit is 0, we put plus, and this is 64, 96, 112, 120 to the base 10. That is the number represented by this sign magnitude representation, 8-bit representation. Well, what about 1, 0, 0, 0, 0, 0, 0, 0? So here we have negative 0 to the base 10 and 0, 0, 0, 0, 0, 0, 0, 0. Here we have positive 0 to the base 10. Okay, so this is why it's, unapplicable or inefficient. Okay, and let's say we have 1, 1, 0, 1, 0, 5, 6, 7, 8. So what's the number represented here? Since this is a 1, that's a negative number. And this is 64 and I think 80, 83. 83 to the base 10. So negative 83 to the base 10. So this is all you have to know in sign magnitude representation. You can try the same thing with, 4-bit representation. So in 4-bit representation, the first bit will be sign as usual. We will have 3 bits for the magnitude, which means it will be from 7 to negative 7. Okay, and in 16-bit representation, the first bit will be for sign and the other 15 bits will be for, for representing the magnitude. So which means 2 to the power 15. 2 to the power 15 is, I think, 32,000 something. Yeah, 32K. Yeah, 32K. Positive 32K to negative 32K. I'm not exactly right here. Okay, I haven't written down the exact values. I'm just giving you ideas. So as the bits increase, you can increase the range of numbers represented, but at the same time, the arithmetic circuits also get complex and complex. Complex, it's not a word, right? Yeah, it becomes more complex. Yeah, that's what I wanted to say. Cool. Yeah, I'll see you in the next video with one's complement and two's complement. Stay tuned.
Thanks for watching the 13th video in our number system series. If you found this tutorial on sign magnitude representation helpful, don't forget to like, share and subscribe for more lessons. Hit the bell icon to stay updated with our latest videos, check out the full playlist to master number systems, and follow us on Instagram. I'll see you in the next video. Until then, keep learning and stay curious. Bye bye.